Electric current and circuits. Learning objectives. Electric current. Producing electric current. Thermoelectricity. Electric circuits. Symbols of circuits. Fuse. Electromagnetism. Electric bell. Electric current. Current electricity exists when electrons flow between two charged objects. We can also say that an electric current is the flow of electrons along a conductor. There are two types of current. 1. Direct current, DC. It is usually obtained from a battery. It flows in one direction only. It flows from negative terminal of the source of power, battery, through conductors, to the positive terminal. 2. Alternating current, AC. It flows first in one direction and then in the opposite direction. It always flows from negative to positive terminals. This type of current is used more widely than DC. The advantage of AC is that its driving force, voltage, can be readily increased or decreased by transformers. Producing electric current. An electric current is produced by creating a difference in electric potential between 2 points on a conductor. This difference exists when one part of the conductor has more electrons than another. The end with excess electrons is the negative terminal, the other is the positive terminal. The difference in potential between these two terminals creates a force called the electromotive force, electron moving force, or EMF, which is measured in volts. Methods of producing current. The two most common ways of producing current are A. Chemically by batteries. B. By induction. C. Current can also be produced by heat, light and pressure. These methods will be learnt by you in next higher classes. Thermoelectricity. Thermoelectricity is the electricity generated by the application of heat to the junction of two dissimilar materials. If two wires of different materials are joined at their ends and one end is provided higher temperature than the other, a voltage difference will arise and an electric current will exist between the hot and cold terminals. Heating effects of current. By using electricity, an exact amount of heat can be produced precisely at the point where it is needed. Electric heating is used in many home appliances such as room heaters, toasters, coffee makers, cookers, cloth dryers. Electric toasters. Electric cooker. Heater. Electricity is converted into heat in several ways. The most familiar method is by making use of the resistance of a conductor to the FL of electricity. Electric current is sent through poor conductor of electricity, called a heating element. Being a poor conductor, the element resists the flow of electrons. In overcoming this resistance, the electrons give up some of their energy in the form of heat. The greater the electrical resistance of the heating elements, the greater the quantity of heat produced. Heating elements. Heating elements are usually made of nickel-chromium alloy wires, nichrome. These wires become hot when a small electric current passes through them. The finer the alloy wire used, the greater is the resistance and hence, greater is the heat produced. You must have seen in the room heaters or cooking heaters long wires, elements, are used which are held in position by porcelain or mica supports. Nickel-chromium alloy wire. Electric bulb. Have you noticed that a lighting bulb when on, gives out heat and you cannot touch it by naked hand? Its filament is made up of a special alloy called tungsten. This is very thin so that it offers very high resistance and electrons passing through it to give away more and more energy in the form of heat. This heat when reaches about 2500 to 3000 degrees Celsius makes the tungsten to glow producing light energy. Electric bulb. Activity 12.1. To produce heat and light. Connect the two dry cells or a single battery with the help of connecting wires with a nichrome coil, through a switch. Put the switch on and observe. What do you observe? The nichrome coil will get red hot after a few seconds, giving out heat and some light. Electric circuits. An electric circuit is an arrangement of electric current sources and conducting paths through which a current can continuously flow. In a simple circuit consisting of a small light bulb, a battery and two pieces of wire, the electric current flows from negative terminal of the battery through one piece of connecting wire, the bulb filament, the other piece of connecting wire, and back to the positive terminal of the battery source. When the electric current flows through the filament heats up and the bulb lights. This is a closed circuit. A switch can be placed in one of the connecting wires. When the switch is open, the connection is broken, so electric current cannot flow through the circuit and the bulb cannot glow. This is an open circuit. Electric circuit. Connecting device. Switch. Output device. Activity 12.2. Closed and open circuits. Diagram A shows both the connecting wires intact, so the bulb's lights, whereas diagram B shows one of the connecting wires broken, so the bulb does not light. Closed electric circuit. A. Source. Load. Conductors. Control. Open electric circuit. B. Source. Load. Conductors. Control. Definitions. Various definitions used with respect to the electric circuits are: conductors. The elements that allow the electricity to pass through them are known as conductors. These include copper, aluminum, tungsten, nichrome, etc. Insulators. Bad conductors of electricity are those elements which do not allow electricity to pass through them. These include rubber, glass, porcelain, wood, cloth, air, vacuum, plastic, etc. Wire insulation. If you touch a live wire, you will get an electric shock, which sometimes causes death. Why does this happen? Because we are good conductors of electricity. Therefore, to avoid these electric shocks, electric wires and appliances are coated with rubber or plastic to protect from shocks. Electric current. The path, conductor, along which electric current passes from the source of electricity is called electric circuit. Complete circuit, also known as closed circuit, is an electric circuit in which electric current starts from one terminal of the electric source, passes through the conductor to the other terminal and reaches back to the source without break, is known as complete circuit. Open circuit. It is an incomplete circuit. In this, the electric current does not complete its journey from one of the terminals of the source to another terminal due to a break in the conductor. Elements of circuit. The devices which are used between the two terminals of an electric current sources such as switches, fuses, wires, etc. are known as the elements of circuit. Symbols of circuit. The following are the symbols used commonly in connection with the electric circuit. SN. Circuit elements. Symbol 1. Conductors crossing with no connections. 2. Junction of conductors. 3. Earth. 4. Aerial. 5. Plug, male. 6. Socket jack, female. 7. Open switch. 8. Closed switch. 9. Heater. 10. Relay. 11. Fuse. 12. Microphone. 13. Heater generator. 14. Neon lamp diode. 15. AC generator. 16. DC power. Fuse. The bulb filament may burn out if too much electric current flows through it. To prevent this from happening, a fuse or a circuit breaker may be placed in the circuit. So, in simpler words, we can say that a fuse is a circuit breaker. It stops the current from flowing through a conductor, hence breaks the circuit. When too much current flows through the fuse, a wire in the fuse heats up and melts, thereby breaking the circuit and stopping the flow of current. The wire in the fuse is designed to melt before the filament would melt. Electric fuse. Before. After. Load. The part of the electric circuit other than the source of electric current is called the load. The load includes all appliances placed in the circuit such as lights, radios, fans, refrigerators, toasters, geysers, heaters and connecting wires. The switches and fuses are also a part of the load. The load forms a continuous conducting path between the terminals of the source of current. Electric appliance. Power, in watt. Fuse rating, in mAh. Electric mixer. 750 W. 3.4. Refrigerator. 120 W. 0.54. TV set. 120 W. 0.54. Electric geyser. 1500 W. 7.00. Electric oven. 4000 W. 16.5. Electric iron. 750 W. 3.4. Overloaded circuit. Every electric circuit has a capacity of allowing a certain amount of current through the elements of circuit. When the amount of electric current surpasses the capacity of the circuits, the circuit is said to be overloaded. What happens when a circuit gets overloaded? Suppose you have a cooking heater with a heating coil of 1000 watts. That means the coil can withstand an electric current to the extent of 1000 watts, and in case you try to pass an electric current of 1500 or 2000 watts through it, the coil will melt and circuit will break. Short circuit. Sometimes, the connecting wires which are running insulated in the same piping may get heated by the overloading of the circuit. The heat will cause the insulation to melt, bringing the live wire and the neutral wire in contact, resulting in sparking. This sparking, known as a short circuit, causes huge fires, damaging valuable properties. Some facts about fuses. Fuses are used to avoid overloading, hence no short circuits happen. The following are the characteristics of a fuse. A fuse is the weakest element in the electric circuit. The fuse melts and breaks the electric circuit to avoid short-circuiting. It is a wire of very short length made of an alloy of 50% tin and 50% lead. A fuse melts when the current flowing through it exceeds its rating. Fuse wire has a very high resistance and a low melting point. Therefore, its temperature rises quickly to melt it. Working of a fuse. Before the working of fuse is discussed, let us first see how fuses are made and where these are placed in a circuit. Placement. Fuse is placed in the live wire, near the point where the electric current enters a circuit. Construction. A fuse is housed in a twin block made of porcelain. The block consists of a casing and a grip. Casing. The casing is a hollow box which is rectangular in shape. It has two brass terminal points A and B on two ends of the rectangle. Terminal A is joined with the live wire and terminal B is joined with a wire that continues the connecting wire to where the electric supply is supposed to go. Thus these two terminals act as the breaking points of the circuit, and current can only pass through the connecting wires when these two terminals get connected. Grip. It is again a porcelain part which is used as the top of the porcelain casing. The two ends of this top are provided with two copper clamps in which the two terminals of the casing fit when the top is placed on the casing. The fuse wire connects the two clamps and thus connecting the live wire with the rest of the circuit when the grip is placed over the casing. Resistance of fuse. Since the fuse is a device for the protection of the appliances we use, its resistance should comfort with the capacity of the circuit to allow the current to pass through it. For this purpose, Fuses of different capacities and resistance are used in different appliances. Cartridge fuse. It is a fuse of fixed value. It is permanently put in an appliance which is very sensitive to the fluctuations of the electric current. Electromagnetism. For a long time it was believed that electricity and magnetism are two distinct phenomena. There was little in common between the two. In the summer of 1820, Hans Christian Ørsted (1777 to 1851), a Danish physicist, made an important discovery. This discovery demonstrated a close relationship between electricity and magnetism. But before this there happened a strange event in 1681. A ship was heading towards Prostad, USA, when it was struck by lightning. The magnetic compass needles showed wild deflections. In 1802, an Italian jurist, Giandomenico Romagnosi, discovered that a magnetic needle was affected by an electric current flowing in a nearby wire. Hans Christian Ørsted. Ørsted's demonstration. During a lecture session in 1820, Ørsted announced that a current in a straight wire caused a noticeable deflection in the nearby magnetic compass needle. He had found that the alignment of the needle is tangential to an imaginary circle which had a straight wire as its center and has its plane perpendicular to the wire. In the figure A, the central dot represents the electric current in one direction. The needle shows the direction of the current towards north, but when the direction of the current is reversed in figure B, the needle also reverses its direction. Activity 12.3. Take an iron nail, a copper wire, iron filings and a battery. Set up the apparatus as shown in the figure. As soon as you connect the two ends of the copper to both nails and the battery, the nail attracts the iron filings kept near it. When the current flows through, the nail is stopped and it moves to its original place. It shows that the electric current was responsible for generating magnetic effect in the iron nail. You may confirm the above phenomenon by compass, the instrument which is made exclusively to detect and measure magnetism. Activity 12.4. Lay a copper wire over the compass which is put on a table. Connect the two ends of this wire to an electric cell. Also provide for a switch in the circuit. Having arranged the setup, switch on the electric current for circulation in the circuit, and observe. You will find that as soon as the electric current passes through the copper wire, the magnetic needle, compass, shows deflection. When the switch is turned off, the electric current stops flowing through the wire, and the needle drops back to its original, the north-south position. Magnetic effect of electric current. Compass needle. Switch on. Switch off. Now change the connections on the electric cell so that the previous plus end becomes dash now and vice versa, and observe. You will see that the needle also shows the respective change in direction of deflection. Now it deflects in the opposite direction to the one in which it had deflected earlier. Both of the above activities help you to understand that the electric current has a certain magnetic effect. The stronger the current, the stronger the magnetic field. A current-carrying coil behaves like a magnet. You have seen in the foregoing paragraphs that a wire carrying electric current possesses a magnetic field. This fact you have read with demonstrations shown with a straight wire. But this also happens when a wire is wound in the form of a coil. Such a coil behaves just like a bar magnet. Activity 12.5. Take a cardboard with a smooth slippery surface. Make two holes in it as shown in the figure and pass a copper wire through it. Hold the cardboard horizontally with the help of a stand so that a battery can also be kept under it. Bend the wire to make a circular coil of it and connect its ends to the two ends of the battery. Sprinkle some iron filings on the board and tap it slowly and gently. Observe. You will observe that as you tap the cardboard, the iron filings arrange themselves in a circular fashion. This phenomenon confirms the presence of magnetic field around the coil. If you bring a compass near the coil, you may see that the two sides of the coil attract different ends, north, south, of the needle. It means that a coil, too, has two poles like a bar magnet. Magnetic field due to a circular coil. Solenoids. A solenoid is made by repeatedly winding a wire to form a coil. A solenoid, being a coil, behaves like a magnet when the electric current is passed through it. We can increase the magnetic field or the magnetic power of a solenoid by placing a magnetic material inside the core of a solenoid. Remember that the wire used to wind into the coil should be insulated. Now, when we pass an electric current through this coil, the core becomes a temporary magnet due to the magnetic field generated by the coil. This results in increased magnetism within the apparatus. Take a small iron rod, it may be the shaft of an old table fan, acquired from an electrician, and wind a length of an insulated, with plastic or cloth, wire to form a tight coil. Connect the two ends of the wire to the terminals of a battery. Bring some oil pour near the solenoid and observe. Uses of electromagnets. There are numerous uses of electromagnets. These include picking up large quantities of magnetic material and transferring it from one place to another. Other appliances based on electromagnetism are ding-dong bell chimes, telephonia pieces, magnetic relay, etc. But we will study in detail the most commonly used electromagnetic device, electric bell. Electric bell. An electric bell consists of a coil wound on an iron core that acts as an electromagnet. Facing the poles of the electromagnet, an armature with a hammer at one end is kept very close. The main parts of an electric bell are given as under. Electromagnet. This is made of soft iron core because only temporary charged magnet is required in the bell. A permanent magnet will keep the bell ringing permanently. This core is wound with the insulated copper wire. One end of the wire is connected to one pole, S, of the iron core and another to the brass stud. Armature. A soft iron armature is connected on the upper end with the gong of the bell. Its lower end has two connections, one with the brass stud through a steel spring and another to the contact screw. Contact spring. The steel spring is fitted in between the armature and the brass stud, which in turn is connected to one end of insulated copper wire. Hammer and gong. A small steel hammer is attached to the armature, at a slight distance from the gong. The gong is made of brass or steel. The striking of hammer with the gong produces the ringing of the bell. Push switch. A push switch is placed between the electromagnet and contact screws. This makes the current pass through the circuit when put on and breaks the circuit when put off. Working. When the push switch is pressed, the charge flows. The soft iron cores become magnets and attract the armature. The armature makes the hammer to vibrate, which strikes the gong and the bell rings. When the push switch is released, the circuit is broken. The armature moves towards the magnet, stopping the vibration in the hammer, so that the bell stops ringing. If we press the push switch again, the process will repeat, resulting in ringing and silencing of the bell. Keywords. Current. Flow of electrons. DC. Direct current, a one-sided current. AC. Alternating current, a two-way current. Fuse. A safety device, a circuit breaker. Conductors. Elements through which current passes. Insulators. Elements through which current does not pass. Tungsten. Filament material used in electric bulbs. Nichrome. Material to make heating elements. Summary. An electric current is the flow of electrons along a conductor. Direct current is obtained from a battery and is one-sided. Alternating current moves first in one direction and then in opposite direction. Electric current can be produced chemically or by induction. Thermoelectricity is the electricity generated by the application of heat to the junction of two dissimilar materials. By using electricity, an amount of heat can be produced. Heating elements are usually made of nickel-chromium alloy wires. Tungsten is the filament used in electric bulbs. An electric circuit is an arrangement of electric current sources and conducting paths through which a current can continuously flow. The elements that allow current to pass through them are conductors. The elements that do not allow current to pass through them are bad conductors known as insulators. Insulation is done so as to prevent from electric shocks. Devices which are used between the two terminals of an electric current sources are called elements of circuit. Fuse is a device to avoid overloading of a circuit. Fuse breaks the circuit and saves from short circuit damages. Electromagnetism is the close relationship between electricity and magnetism. Temporary and permanent magnets can be easily made. Electric bell is a common appliance based on electromagnetism.